Hi guys, this is Mrs. Allison. Today we are going to continue the idea we started yesterday with double integrals, but look at one other detail that goes with that, and then talk about average value of our double integrals. So I would like you to hit pause and try the first warm-up. I know I wrote warm-up number 2, but I think we're going to go over that together. If you want to try it and just see how you do, that would be fine as well. But hit pause, try warm-up number 1, and then we'll come back. All right, for this first integral, the double integral of y sine xy over the region from 1 to 2 and 0 to pi, the way I chose to set this one up, and I'll explain why I chose to set it up the way I did, is I set up the integral, let's do from 0 to pi, and then from 1 to 2 of y sine xy dx dy. Okay, so let's look at this integration. We're going to work from the inside out. So I'm going to start with this integral here. And taking the integral of that, 0 to pi, this piece will become, let's see, sine negative, okay, so we would get negative y cosine xy over y, evaluated when x is from 1 to 2. So simplifying that piece, we would get, let's see, we would get negative cosine 2y minus negative cosine y, so plus cosine y, dy. So now I'm going to integrate this, and integrating this we get, let's see, negative 2 sine 2y over 2 plus sine of y, evaluated from 0 to pi. Lovely. We do all this and we get, that is going to be 0. Great. So this is 0 plus 0 minus 0 plus 0. So then we get just 0. So there, the net volume of y equals sine of xy over that rectangular region is just 0. Now what about the other way? Had we set this up the other way, I'm going to scroll over just a little bit. Had we set this up the other way, we would have had the integral from 1 to 2 and then 0 to pi of y sine of xy dy dx. And when we do this piece, if we look at just this piece with respect to y, that means x happens to be a constant, y happens to be my variable. So I've got this product rule. So with the product rule, I'm going to use integration by parts. So we would have to let u equal y, so du would equal dy, and dv would be sine of xy dy, which means v would be, like before, negative cosine negative cosine of xy over x. Yeah, yep. And so then when I go to look at this integral, and I'm just doing the inner part at the moment, I would end up with negative y, so uv minus the integral of v du, and v would be negative cosine xy over x v du dy. And you lost me. This proves to be quite a bit more work. Could we get there? For sure, we can get there. But looking at the other method, it looked easier to me, and so therefore that's how I did it. All right, let's look at the next example. And I know I said warm up, and do I think you could figure it out? Sure. But we haven't really talked about what this means. The volume of a solid bound by the elliptical paraboloid. It really not much different, but we want to change one thing. What we want to change here is that we need to think about what our function is and then what our bounds are, and write it that way. So it says that our height is represented by this elliptic paraboloid, that x squared plus 2y squared plus z equals 16. Well, as a function, the height of my prisms, the height of my surface, can be rewritten as z equals 16 minus x squared minus 2y squared. This is going to be my function. Remember, f of xy is just another way of writing z equals, that third variable equals. And so there is my height. Now we need to think about our bounds. Now our bounds for this one says the planes x equals 2, y equals 2, and then the 3 coordinate planes, meaning it's cut off at the coordinate, like the axes marks. So when I write my bounds, I would get from x is between 0 and 2, and then y is between 0 and 2 as well. So now when we set up our integral, and again, this one can go either dy dx or dx dy. I happen to do dx dy, you can choose whichever one you would like. So if I set this up 0 to 2, 0 to 2, my bounds don't actually look any different either way I set it up. What will matter here is which one I write first, and I happen to write dx first. So let's go through and do this integral with respect to x. So with respect to x, let's just rewrite this. With respect to x, if I anti-differentiate this, I would get 16x minus x cubed over 3 minus 2y squared x, because remember y would be like the constant. And this is going to be evaluated when x is equal to 0 and x is equal to 2 dy. All right, so plugging in 2 and 0, let's see what happens when we plug in 2. 2, we get 32 minus 8 thirds minus 4y squared. Plugging in 0, we get 0, so it would be minus 0, so we're just going to leave that. And now this problem becomes an integral with respect to y. Let's simplify it. 0 to 2 of 32 minus 8 thirds. So 96 minus 8 would be 88 over 3 minus 4y squared dy. Okay. Now, well, this was that inner integral. That's fine. Now when I anti-differentiate this, we get 88 thirds y minus 4y cubed over 3, evaluated from 0 to 2. So we get 88 thirds times 2 minus 4 thirds times 8 minus 0 minus 0. We'll just minus 0. 176 over 3 minus 32 over 3. We get 144 over 3, which means that the volume under the surface, that elliptic paraboloid, between the planes, if we look at the region, the planes x equals 2, y equals 2, and the 3 coordinate planes, is 48. How do you do? Okay, so let's just talk about one more concept. Let's look at the idea of average value. We know from calculus, from single variable calculus, that the average value is equal to the integral divided by the interval. If we were to look at a visual of this, we maybe would have seen we have some curve and we have the area that we're finding between A and B. And we know the area under the curve is this shaded region. Let's do that like this. So this is the area under the curve, right? If we took the integral from A to B, that's what we'd be finding. And remember the average value, I don't know where it is exactly on this one. Maybe it's right about up here. Maybe not quite there, maybe a little bit higher. Says that if we were to take the area of this rectangle, that area would exactly represent the area under the curve from A to B. So the area of the rectangle from A to B would represent the area of the curve from A to B. And remember, that was average value. Well, if we want to find the average value of a function in 2 variables, okay, over region, if we let A equal the area of the region, we'll call it the area of region R, then the average value would be 1 over A, 1 over the area of the region, and then the double integral of the region of f of x, y, dA. This would be the average value. Looks pretty similar. We just have that double integral and understand that we're looking for the interval is no longer an interval because we're in 2 space. We're no longer in 2 space, we're in 3 space, so it has to be an area. All right, so let's look at an example. If we want to find the average value of the function, which is x squared y, over the region that has vertices of -1, 0, -1, 5, 1, 5, 1, 0. So really this is a rectangle where we have these coordinates. So we are at -1, 0, 1, 0, 1, 5, and -1, 5. So the surface is above this region. So this is the region. And above it we have this surface, the x squared y. And we want to find the average value of that. So to do that, one of the things that I need to do is I need to find the area of the region. It's going to be quite easy because this dimension here is 2, this dimension here is 5, so the area of the region is 10. So when I set up my integral, it would be 1 over 10. The integral from, well, we need to think about our bounds. So depending on if you want to do dx dy or dy dx, it really doesn't matter. And actually, we're going to look at this one because it follows that idea we talked about yesterday. So if we set it up this way, here's what I want you to notice. You'll notice that when I can separate these, I have an x squared dx, dx, and I have a y dy. So if you recall from yesterday, this can actually be set up using that last theorem or property we talked about yesterday. And I know that the bounds that go with the x, are the -1 to 1. And the bounds that go with the y are from 0 to 5. And so I can set this up using those like this. (0 to 5, y dy). So we have the integral from -1 to 1 of x squared dx and the integral from 0 to 5 of y dy because they are functions that can be separated. So now all I need to do is take the antiderivatives of each piece of those. So this would be x cubed over 3 evaluated from -1 to 1. And then this one would be y squared over 2 evaluated from 0 to 5. So we get 1/10 of, let's just do 1/3 minus, that would be -1/3. And 5, when we plug that in, 25 over 2 minus 0. And so then we would get 1/10 of 2/3 of 25 over 2. And so multiplying these, we get 25 over 30, or 5/6. So we know the average value of f over the region R would be 5/6. All right, so hopefully you're feeling pretty good about double integrals over a rectangular region. And next time we meet, we will talk about more general forms over general regions. Have a good day.